Hi, I'm Meta Spencer, and today I get to see some of my old friends. I've become, over the last few years, very preoccupied with climate restoration and climate repair. And so I've made a lot of friends who are also in that angle. And today we're going to talk about a new proposal. I guess it's sort of new anyway. I haven't heard about it. Having some relationship to something I have heard about, which is ocean iron fertilization. But our main proponent of this new angle is a good friend, Peter Fiekowsky, who's an American physicist, author, and founder of a field in climate restoration. He had a book called Climate Restoration. And in Australia is Robert Tulip, Robbie, we call it, who worked for many years for the Australian government in international affairs and trade. He's the founder of Iron Salt Aerosol and some kind of climate restoration startup. And he's a chaplaincy manager of the Australian National University. Different interests. And Brian van Herzen is also in Australia. He's an ocean scientist and engineer and the founder and executive director of a nonprofit organization, the Climate Foundation, which is an institution working to regenerate life in the world's oceans. So welcome, gentlemen, and I'm so glad to see all of you. Happy New Year. I'm going to give the floor right away to Peter because I think you're the guy with the new angle. And everybody's going to be talking about what you're doing that's a little different from the ocean iron fertilization angles that we have sort of become familiar with. So, Peter, hi.
Hi, Meta. Hi, Bobby. Good to see you again. Brian, we have our normal call half an hour from now, so good to be on half an hour early and in an organized conversation. So, Meta and your audience, you know, I'll say a little bit about ocean fertilization and the whole context. So climate restoration, for anyone who's not familiar, is the idea that we want to give our children a safe climate, safe CO2 levels like we were given 50 roughly years ago. And it's a wonderful idea. The good news is nature removes about the same amount of CO2 that every time we have an ice age, and many times during an ice age. It's about 1,000 gigatons of CO2. And we figure that because nature has done it many, many times regularly, and there's no evidence that it's not safe from the geological history, we figure we can probably do it and probably do it safely. So then the question is, well, how does that work and how do we actually do it? And in 1990, Dr. John
Martin.
We figured out that the main source of the carbon removal during the ice ages is phytoplankton growth in the ocean. Just like all of us know that trees grow on land, in the ocean, which is much larger than the land area on the planet, phytoplankton grow, which is phytoplankton is what makes oceans green. And when the carbon produced from the phytoplankton falls deep in the ocean, maybe over a kilometer deep, then it's essentially permanently stored carbon for thousands of years. And so the method that nature uses to make that process happen of growing the phytoplankton is iron. So it's called ocean iron fertilization, OIF. And that's been discussed and studied since the late 80s. And it's become it's always been controversial from the first beginning of it because it sounds like geoengineering. It sounds like someone who wants to change the atmosphere on our planet, which of course we do. We want to bring the atmosphere back to what it was 50 or 100 years ago. And so ocean iron fertilization has been studied by scientists for certainly 35 years, but quite intensely for the last 25 years. And it's been written about as a whole basin ocean fertilization. And the reason for that is that to get enough CO2 removed, the scientists assumed that someone would do it over the full ocean or the relevant parts of the ocean that are low in iron, which is probably most of the ocean, depending on how you look at it. And what they realize is that when you grow phytoplankton, typically 1 or 2% of the phytoplankton that grow end up sinking into the deep ocean. Primarily, yeah.
I'm never sure I've ever heard anybody explain why any part of the ocean is low in iron.
So if you think about iron, it sinks. And the bottom line is the only source of iron in the ocean is primarily dust from dust storms and volcanoes. And when it sinks into the deep ocean, it doesn't come back again. It doesn't dissolve like most minerals do.
And those areas where there's a deficiency of iron, there's also a deficiency of the phytoplankton growth, right?
Yeah. If iron is below a certain level, nothing grows.
It's called high nutrient, low chlorophyll zones, and they're estimated at about 20% of the world ocean, classed as ocean deserts, which are growing. And another major factor in ocean deserts is the ecocide of the whales, because previously whales retained a lot of iron in the biomass in the surface, but human killing off of the whales has destroyed a lot of the ocean ecology, and so Peter's work is aiming to restore ocean ecology.
Thank you.
Yeah. So most of the ocean is low in iron, and and putting iron in most cases will cause phytoplankton to grow. So the innovation here is we looked at the history, and I'll show you a little bit of data, but we looked at the history and realized that most of the iron that's removed is removed in downwelling eddies. And so what's been realized is, as I said, about 1 to 2% of the biocarbon produced in the phytoplankton or algae, more or less the same thing, falls into the deep ocean normally. But if you have a downwelling eddy, and a downwelling eddy is a big, essentially like a high pressure system in the atmosphere, you have a rotating mass, and it produces through the Coriolis effect, it pushes it down, just like a high pressure system pushes air down. If the water rotates in the same direction, it pushes the water down. And in that case, it pushes the water down, and the biocarbon sinks before most of it gets eaten by fish. So if there's no downwelling eddy, 98% of the carbon gets eaten by fish, which then metabolize it and essentially exhale it back to the atmosphere over some number of weeks, months, or a year. If you have a downwelling eddy, now you remove lots of CO2, and so there are two aspects of what we're calling localized ocean fertilization. It's localized because the active part is happening only in the downwelling eddies. That's the localization. Then the second aspect is when you add enough iron to the ocean, in addition to phytoplankton, which use nutrients, especially nitrogen, it also grows cyanobacteria, which fix nitrogen and essentially fertilize it. And this is the same idea that where farmers will grow beans and rice, let's say. And so the beans will fix the nitrogen, and the rice and the corn need that nitrogen. And so providing about 20 times the iron concentration needed by phytoplankton will let the cyanobacteria grow and fix the nitrogen needed. And so now you can...
Cyanobacteria sounds something nasty. I thought that's what we don't like. It kills us, doesn't it?
Well, everything kills us. My wife is a nurse practitioner, and she worked in pharmacology for a long time, and she said, uh, I forgot the terminology. Dosage is everything. So water in a high enough dosage kills you. Everything. And so
But so we don't have anything really against cyanobacteria.
no, every time you grow beans, you're growing a lot of cyanobacteria in the ground.
Well, I think cyanobacteria are specific to the ocean. There's, some plankton are cyanobacteria. They're important for a healthy ecosystem in the right abundance. That's one of several types. Thanks.
Yeah, yeah. The three key points, well, the two to three key points of uh, localized ocean fertilization. One is inside the downwelling eddy, so the carbon is removed. Second is provide enough iron over a long period of time to grow the cyanobacteria. It takes several months for them to multiply. They grow much more slowly than most phytoplankton. In part just because the chemical reaction involved is much more difficult when you're uh, when you're fixing nitrogen. And then the third aspect of it is in terms of utilizing it is it removes so much CO2 that you can now measure the CO2 removed by seeing the reduction in the atmosphere. And we've demonstrated that with satellite data from the NASA Orbiting Carbon Observatory. So those three factors together mean several things. First of all, it's much safer. So the no one's ever really proposed doing full basin ocean fertilization. It was just a concept. Hundreds and hundreds of articles criticizing full basin ocean fertilization, and zero articles recommending doing it because turning the whole a large part of the ocean into pea soup, thick green, luscious, just is clearly nothing that we want to do. And doing it would cost probably a quarter of the whole global GDP. And we don't have, A, we don't want to, and B, we couldn't afford to even if we did. So localized, meaning we're just doing it in these less than 1% of the ocean, which are these large downwelling eddies. Now, the lush green areas that would be produced, just like farming, are limited. And then when the eddy disappears or you stop fertilizing it, it goes back to natural situation with low phytoplankton, which is, whether it's good or bad, it's just the way nature goes. So it has very low impact. Then so that solves the problem of just broad scariness. The second advantage is reducing the amount of nutrients robbing. And so one of the concerns about doing full basin OIF is that if you're producing that much phytoplankton, you're going to be stealing nutrients from other parts of the ocean, depending on how the currents flow. And there was a very famous study at MIT which showed that in the model they did, if you do enough phytoplankton growth in the Antarctic, then eventually, given the currents in the Baltic Ocean, a whole other side of the planet, you could see some reduction in phytoplankton because there's less nutrients in the ocean where the water came back up. That gets canceled out because in localized ocean fertilization, it's not focusing on sinking the phytoplankton. The phytoplankton takes CO2 from the air and it takes the CO2 into biocarbon, and then the biocarbon gets mostly eaten by animal plankton called zooplankton, and it sinks. And the biocarbon eventually, when it gets below about 3 kilometers, dissolves and becomes mostly bicarbonate. Now, what's interesting is even when we remove all 1,000 gigatons of CO2 into the ocean, and that becomes increased bicarbonate, the bicarbonate level would increase about 1 to 2%, probably 1.25%. So it's very small, even after we remove all of the excess CO2, the increase in bicarbonate.
The whole ocean.
Yeah. But, and especially,
you mind if I ask a question about this nutrient robbing
yes.
aspect?
Yeah.
The thing that I find implausible about that criticism is when you look at the size of the world ocean, it holds about 1 billion cubic kilometers of water, and most of that water is in the deep. That's below the thermocline.
Yeah.
So the top water has low nutrient, but below the thermocline there's really high nutrient. So if it's possible to get some of that nutrient from the deep ocean water and bring it to the surface, then the idea that oceanine fertilization will be robbing nutrient from one part of the ocean. There is so much nutrient in the ocean. If we can make use of that deep ocean nutrient, as Brian has done with his marine permaculture work, then that whole concept of nutrient robbing just doesn't seem to make any sense.
Oh, absolutely. I think everybody agrees with you. The point, I believe the point of that MIT study was that it's possible, and that he was able to do computer models in which he was able to measure a change. He didn't claim that it was likely. He just said it was possible, I believe.
Yeah, usually when the field talks about nutrient robbing, they're referring to the top 100 meters of the ocean, which is oftentimes nutrient limited. There is an energy barrier since that top layer is warmer than the deeper water. And so it takes energy to bring the nutrients up from the deep. That top 100-meter layer is considered the mixed layer, if you will, and plus or minus depth-wise. And they're worried, the worry is that if you intervene somewhere in an eddy or something, that a downstream ecosystem gets robbed of nitrate or phosphate or other nutrients. So that's commonly the way they talk about nutrient robbing. And I agree with you. There's plenty of nutrients in the bottom, and it's about having a good supply of macronutrients, nitrate and phosphate, and also the micronutrients, which include iron and other things, to ensure that we can really restore the level of primary production by plankton in the ocean. We're down 30 or 40% in the subtropical and tropical ocean already, and it's getting worse. And that's really an indication, it's moving us towards a Permian mass extinction where we lose the productivity of the oceans. That's what's at risk. Thanks.
Yeah.
Yeah, so Peter's published his Substack article explaining why local iron fertilization is vastly better than broad scale ocean iron fertilization, and I actually found it a really great summary of your work, Peter, and just extremely interesting. So well done for pointing it out. One of the things that I found in that article of a lot of interest was that you said that the reputational problems relate to scale and side effects, but in my sense is that the reputation problems are much more political, that there's just a political objection to anything that would slow down, that would reduce the focus on emission reduction as the sole agenda. And so because people are so fixated on cutting emissions, they look at ocean iron fertilization and say, oh, look, it's actually a better way of addressing the carbon problem than cutting emissions. And so, because people are so fixated on cutting emissions, they don't want to allow any alternative to even be studied.
Yeah, it's interesting. The politics are fascinating. Last year I spent quite a bit of time talking with the U.S. Congressional Science Committee on this topic, and they said exactly what you said, that politically in the U.S. Congress they were unable to discuss publicly restoring the climate because for that reason, that if they did that, then they were afraid that some people would think that it would let oil companies off the hook and and allow them to sell us oil, allow us to buy oil from them, which didn't make any sense. But yeah, my solution to that, Robbie, is to separate these issues into separate parts. And so the transition to clean energy is something I think everybody likes. If you've stood behind a diesel bus, then you remember what that's like to get the pollution from fossil fuels. And everyone, even people who make their living from fossil fuels really would prefer to have electric buses, which are quiet and smell good and so on. So, but separating that into one topic and then CO2 level into a separate one, because what's nice about restoring the climate is it's not really an issue. That is to say, the UN has expressed no interest in restoring the climate. The UN goal is to get to net zero. And of course, net zero is the first step of getting CO2 levels to fall. But, I've given...
Well, it's not, of course, actually, Peter, because there's a lot of people who think net zero is the end goal. But really, net zero is just a milestone towards a stable climate with restored Holocene CO2 levels, ultimately.
Right.
But net zero just leaves us with a temperature 3 degrees above baseline. It's quite by itself. Net zero is nowhere near enough, and that's why technologies such as climate restoration with ocean ion technologies are just so central to stabilising the climate. Do you mind, Peter, if I just ask Brian to comment? He's had his hand up.
Thank you.
Oh, yeah.
Yeah, I think none of these interventions are an excuse to not move forward with all three legs of the climate triad, and that is emissions to zero, 2,400 gigatons of carbon removal, and some degree of climate repair to keep our civilization on track while we're getting our carbon budget back into balance. One of the real benefits of Peter's proposal for local interventions is that there are 1,000 local and state governments that could approve this kind of regeneration of primary productivity, which of course helps fisheries. It helps economies, it helps coastal economies, and it really helps restore fish populations that have been depleted both by overfishing and by ocean warming. And so I think there's a great chance to move forward and make progress locally and regionally with both carbon removal and climate repair strategies. And that's, I think, one of the main benefits of Peter's local proposals.
Yeah, thanks. Yeah, and so Robbie, just back to the objections that most people don't think about restoring CO2 levels, and so what we're finding as I give talks is that absolutely no one opposes it. The congressional concern was they didn't want anything in U.S. law regarding that, again, because that would bring up political issues, but they were fine with it if it's done informally. Because as long as you get to net zero, then you fulfill the UN goal. What happens after that, no one really discusses, right? No one says you shouldn't reduce it.
Well, you're discussing
it. That's right. But it doesn't need to be a big discussion. And what we're finding this year is there's really very little political interest in it. In Canada, that could be different, but certainly in this country, there's no political interest one way or the other. On the other hand, the real impetus is going to be, it looks like it's going to be the companies that are building all these AI server farms, that they need literally millions of tons of carbon credits because these companies are, have their reputation are based in part on their net zero promises that vary from 2030 to 2060. But to get to net zero, they need literally, collectively, 100 million or so tons of CO2 emission credits. Well, the only way to do that is with the localized ocean fertilization. And so we're now one of the projects we're working on is putting together a structure so that they can verify the removals, which is pretty easy. You can see it in the satellite carbon information as well as
Well,
in
maybe not
local.
the only way, Peter. Like, I think that there are other large-scale carbon removal potentials, but I think that your suggestion is one of the best. But like, so, for example, Brian's work on marine permaculture with seaweed arrays is a fantastic way of sequestering
Mm,
carbon, and so it's distinct from just an iron focus. But
yeah.
what I'm
Well,
interested in,
let me
go on
put
and
a nuance
respond
in
to
there,
that, please.
and that I've been a big fan of Brian's seaweed, and those who've read my book know I'm a big fan of synthetic limestone. The problem is that the price and the growth of those is slow, so they're important. But for a company that's building server farms right now, they need credits in the next 2, 3, 4, 5 years. And the only way to scale something up that 100 million tons in 4 or 5 years is apparently the only known way to do it that fast is with the localized ocean fertilization.
Let
Yeah,
me
I would hesitate to say that's the only way, but it's certainly one of several ways. Go ahead, Meta.
yeah, I
Well,
want to
we should talk about that later. Yeah.
I just want to make sure understand where we are. I had assumed that when you're talking about local iron fertilization, that you have some new angle, some new technology. But my inference is that you're not really doing anything that different, or you're not proposing it, but that you're simply proposing that you do it in specific places where it'll be more
Yes.
efficient and so on. And so it isn't a new technology exactly, but you're specifying where it should be done. Now, if that's the case, I believe the only debates that would be arising would have to do with safety issues. People, I would think, would be very interested in what side effects there might be. So I'm sure that you have a ton of scientific predictions or research that you can bring to bear on that. Is that the next step in, we've got half an hour left. Is that the next step in our conversation to consider how safe your proposal would be?
Yeah, I think it may be a quick conversation. The summary I always give, and Brian and Robbie can add nuance to it, is we've had 1 million years at least of ocean fertilization from dust storms and volcanoes and whales, and there's no actual reports of safety issues, of real safety issues, and so that's a good sign that there's nothing has been reported that's of note so far. Um, you know, doing it intentionally, we could get higher concentrations of phytoplankton, but because within a limited area and the eddy keeps it contained in that area, if there suddenly were a bad outcome, let's say there was uh, somehow a phytoplankton of some dangerous type was growing, that would die off quickly. And because it's a downwelling eddy, the phytoplankton would die and get sunk into the depths where it dissolves into the basic chemicals again.
Well, now,
So
my recollection is that 15 years ago, there was an experiment off the coast of Canada. Some Indians recommended, Haida, I believe, experimented with ocean iron fertilization, and the Canadian government put a stop to it. I presume that because they thought there might be some side effect. Remind me what actually happened.
Well, I don't recall any reports of side effects. There are there's something called harmful algal blooms, HAB, harmful algal blooms, and red tide is an example of that. Those are coastal effects, and they happen pretty regularly along the Pacific coast. And I believe that at some point after that event in 2012, where they added about 100 tons of iron sulfate to an ocean eddy about 200 or 300 kilometers off the coast, that there was a harmful algal bloom. There's no indication that the two are related, but you know, how to say it, although uh, uh, they
But
happen
there
at the
was
same
also a
time.
really big increase in the salmon yield, and the proponents maintained that those were related, but then that's disputed. But
Right.
yeah,
Yeah. You can never prove anything. You can only disprove things.
Well, to
So,
provide some color on that, it was century record salmon catches off Canada, Washington, and Alaska. So it's like they got more salmon than they'd gotten like 1899. So it was blow the charts in terms of the productivity. The harmful algal blooms are normally happening at high water temperatures, so that's complex. But I track the Haida Gwaii Salmon Restoration Company work closely, and one of the main effects were this 2 years later, seeing these very record number of salmon that were caught.
which
And
was
so
the intent of the project.
that was the intent. I think there's open now. That's arguably in a high nutrient, low chlorophyll region, like you're talking about, Robbie, and that's maybe 10% of the oceans. There's a case to be made there, and that's something to be done at local and regional scale. And then I think separately we should look at the other 90% of the ocean and consider what some of the potential side effects could be there.
yeah, this is a graph of the Alaska salmon catch in terms of number of fish, and the Haida test was done here. Next year, about a 4 or 5 fold increase in the pink salmon, which is the pink, and then every other year ever since then, there's been this burst. It's been slowing down, but it's been, as you said, Brian, most remarkable.
Yeah, it is. And by the way, it's a 2 year life cycle for those pink salmon. So it really helps to explain. Some of them are 2 years, some of them are 4 years, but that explains why you get this ringing impulse response occurring.
So when they dumped that iron, it didn't all get used up within 1 year. Several seasons later, there are still implications from doing that. Is that right?
Well, I think part of this is the reflection of the salmon population. When you get this huge bumper crop of population, they're going to breed and spawn. And then 2 years later, you're going to get another big crop of salmon because you had such a large, population of juvenile salmon from 2 years ago.
I see.
And you shouldn't really use the term dumping because it's
Yes.
been very controversial. Because what happened after that, there was a whole series of major scientific studies of ocean fertilization by academic bodies, and then this 2012 one was sort of outside the academic context, and so the universities really objected to that. But and so the London Protocol in the United Nations defined ocean iron fertilization against this whole context of dumping of waste, which is very controversial and very contentious, because if you're fertilizing the ocean in order to improve it, then how can you call that dumping of waste? So it's there's a big debate, and what it suggests is that a lot of the claims about safety that you are asking about, Meta, are really straw man arguments. That people have said, we want to stop this whatever way we can, and so we're just going to clutch at whatever arguments are convincing to people, regardless of whether they're true. Because what we should be doing is we should be saying to people like Peter, okay, how can we get the investment? How can we get the permissions to test these hypotheses? Like, we don't just ban the hypothesis. We say, okay, this has got great potential for restoring the climate, which is really important. So let's put the money into it. If it doesn't work out, then we don't keep going. If it does work out, then we expand it.
Mm-hmm. And one of the real criminal things that occurred is the government destruction of the water samples and the data. It was very telling, right, that the first actions by the government was to destroy the water samples and destroy the data, so that
this was from the 2012 HADA project.
That is correct.
Why?
And so,
What did they have against it?
It undermines the argument about emission reduction, because it's such an efficient way of removing carbon from the air at a very low cost and environmental benefits. When people are saying we need to subsidise emission reduction through renewable energy, then if there's a better way of fixing the climate, then those people will say, well, we can't do that. That's my understanding of the situation, which is, I know it's a bit of a conspiracy theory, but that's how I've come to understand it, unfortunately.
and to be clear, I think we can recommend all three, and that is, we need emissions reduction, we need carbon removal, we need climate repair, and the scale is key. I mean, Peter mentioned the dose defines the poison, and I think we've got a long way to go just to get to 1 gigaton. Nature, naturally, the marine snow naturally sequesters more than a gigaton of carbon each year. I think the oceans overall, until we get to gigaton scale, I mean, there are demonstrable systems in the ocean with microalgae and macroalgae that provide gigaton scale carbon removals annually. And until we get to that gigaton scale, the question of what's sustainable is really academic. I think what's more important is to enable and do the early applied research and development to enable these approaches to be refined. And then once it can get up towards gigaton scale, then it can be a societal question of whether the sustainable removal is 1 gigaton or a dozen or 50. I think that's something that we need to move forward with. But let's get to the gigaton first. Let's support the applied R&D with university partners and independent observers to be able to confirm and validate the results, as we're doing in the Western Pacific right now in the Philippines with 4 university partners measuring the carbon cycling under marine permaculture platforms. The same can be done for mesoscale iron trials, and that really should be done, because ignoring it is the worst thing, because at some point some country is going to do it. We better know what happens when that occurs, so that we know what the side effects are and could address those and understand them ahead of time. Thanks.
Yeah. And I thought it was extremely interesting what Peter was saying about the artificial intelligence industry as a key constituency of support, because there's both the agenda of offsetting the emissions from data centers, but there's also the really strong potential for artificial intelligence to help us with the policy conversation. Like, feeding this conversation that we're having today into ChatGPT and just asking for its opinions about it, it really helps to refine the arguments and helps us to assess these risk concerns and also how to do it. There's such great potential to mobilize AI to enable us to solve climate problems, and so important constituency of support with potentially with money to both lobby for permission and to work out how to do it better.
Okay, what do you have to do? Who is the obstacle? And is it really an obstacle, or are people just scared to antagonize certain powers that be? Because I don't think there's any kind of international law that says anybody who scatters iron in the ocean has to go to prison for their rest of their life.
Yes, there is. There's the London Protocol defines the addition of iron to the ocean under its category of the prevention of dumping of waste. So and also the Convention on Biological Diversity has agreed strict limits on these technologies, which have sent a great chilling effect over the last decade, so that there's been no field experiments of the sort that Peter is proposing since 2012.
Well, is
Now,
there
there's
then for these universities to forge ahead anyway, or is this thing really an ironclad prohibition?
well, they're recommendations. So, but both of them are suggestions that nations could produce laws and enforce them if they like about it. So it's been confirmed both by the National Academies of Science in the U.S. and by the Columbia Climate Law Center that there is no enforceable law. That you're correct, Meta. That no one is. There's no way to put someone in jail at this point for doing it. Now, for public opinion, you've got to go get approval. The last thing you want to do is something like this without public support. But you ask Meta, who's opposing it? And I've been studying that for a long time. And essentially no one, as you were saying, Meta. Everyone wants the safe climate for our children. The fact that ice ages happen is quite clear to everybody that's a safe process for removing large amounts of CO2. And as Brian said, can it be done quickly? Is not too. There's not. It needs to be tested. But as I said also earlier, there's so far no evidence that you can do it too fast. We want to check for it. But here's the good news, is that when you're doing any engineering project, you always start small, what we call a minimum viable product, or the minimum viable project, just to answer the most difficult questions, and then build gradually from there. You don't have to enforce that because you cannot build, a 2-kilometer suspension bridge, unless you start with 100 meters, then 200 meters, and 400, and so on. That's the only way you can do the engineering. And the same is going to be true for localized ocean fertilization. We're going to start with probably a 30-kilometer or 50-kilometer eddy, and then 100 kilometers, and then probably 200 kilometers, and then 300. And my feeling right now is that we'll stop at 300-kilometer eddies and then go to multiples of those. So the first step is to get the permit. Even though it's not absolutely required, it is essentially required. And so getting the permit, getting the sensors, because we'll be measuring CO2 from buoys surrounding the area. What one of the things I love about this approach is you don't, in the beginning, you don't need to do deep ocean sampling. The first tests, you can just measure the CO2 in the air as it blows across the ocean. When it blows across the area where you grew the phytoplankton, the CO2 is going to go down. And it's been measured about 40 to sometimes even 80 parts per million reduction as the wind blows across this section of ocean. And that can be measured easily with 6 or 12 sensors in a circle, catching the CO2 upwind and then downwind. And that's inexpensive, can be done quickly. Once that part is mastered, which would probably take 6 or 10 months, then you can do it at a small scale and figure out how to master the growth of the cyanobacteria to make sure that we have a continuing source of nitrogen. And by that time, we'll be producing enough CO2 removal that will have a source of income from people who need the carbon offsets. And then the relatively expensive process of measuring what happens in the deep ocean and even on the ocean floor can be done. But you can do it step by step by step. And the point is, you don't have to enforce that. You hardly even need to talk about it because it's the only way it can be done.
Mm-hmm.
I'm glad that that Peter mentions the ocean floor. And I think if done diffusely on this 100-kilometer scale, it could have minimal effects. The oxygen supply in the deep ocean, particularly the ocean floor, is important. It normally comes from the Antarctic bottom water. If done at low concentration, it really mimics the natural marine snow that occurs or has occurred pre-industrially. But in an ocean warming world, we're losing a lot of that primary production. So in many ways, Peter's proposal would help to restore the level of plankton in the tropical and subtropical ocean locales or regions. We see a lot of evidence of declining productivity there. And the challenge is then we want to be able to measure the deep oxygen level. So that's one of the things to ensure safety, is to measure that deep oxygen near the seafloor, make sure it's not going down too much. One of the real challenges we're seeing is that deep oxygen supply from Antarctica is diminishing a bit. The Antarctic bottom water is slowing down. That supplies about half the deep oxygen to the world oceans today. So it's good to, in terms of speeds and feeds, let's keep a monitor on that deep oxygen while these trials are taking place. There's no substitute for doing real field trials. I've got to applaud Peter's efforts to do some ongoing deployments and really, begin the important applied research and development that needs to be done in this decade to address the safety of this approach and the efficacy of this approach while at small scale before it gets tried by some country in desperation in the future. With or without the research.
Really got to cover that. We've got 10 minutes left with Brian. Peter has cited the Mount Pinatubo eruption in 1991 as a really important source of evidence for the effectiveness of the proposal, and some people have been there's been questions about what was the cause of the CO2 pause after Pinatubo, and Peter, do you mind telling us a bit about that?
Yeah, so it starts with the data, and the graph here is CO2 levels before and after the Pinatubo eruption, right in the middle. And you can see the CO2 level in blue measured from Mauna Loa. This is the Keeling curve. You can see it going up steadily. And then you can see it was stable for about a year and a half, and then went up steadily. Now, this peak here is the big 1998 El Nino. But what's with El Ninos, it starts with with less CO2 levels, more CO2 levels, and when all is said and done, it comes back. And you see the same thing in the El Nino here, and another one here. So you can the difference in these two curves is 2.25 parts per million, and that's about 17 gigatons of CO2. Now, there have been a lot of proposed pathways for how did the 17 billion tons of CO2 disappear, and they all fall apart. Several of them related to the fact that there was a lot of dust thrown into the stratosphere, and that produced some diffuse light. It reflected a lot of light into the space and cooled the planet by 0.5 degree for a year and a half. And those theories are interesting.
I always heard it was the collapse of the Soviet Union.
Another one was the collapse of the Soviet Union. That's right. That did reduce emissions by about 1%.
Really?
But this is a 100% difference. Oh. So that's about 1% of the impact. And so, but the main thing is that this effect has never been seen in any other eruption since the Keeling curve was produced, and so that indicates to us that it had to be phytoplankton. And when you do the math, the amount of dust that was strewn beyond 1,000 kilometers was absolutely negligible. The reports were that in Vietnam, about 1,000 kilometers away, downwind of the eruption, there was just a bare touch of dust, a minimal amount of dust, and there's no reports whatsoever beyond a few parts of Vietnam. And so, we're confident that it was only in the downwelling eddies around Mount Pinatubo that the phytoplankton grew. And there were no reports of damage on the seafloor there. There was 17 billion tons of CO2 removed, and I don't know what studies were done. There were a lot of studies done on the ash on the seafloor, and how that ash affected sea life down there. But there are rumors that there were studies, but I haven't seen any studies about in the following years, in the following year and a half, if there was any significant impact. Obviously, if there had been, we would have heard about it.
And so the Pinatubo ash had a high iron content.
Most eruptions have about 3% iron. So whether Pinatubo is high or low, I don't know.
But you would not attribute it to any other element besides iron.
That's a good question, Meta.
Yeah.
Because the limiting nutrients typically are described as iron. You put iron in, and immediately, in many parts of the ocean, you get rapid phytoplankton growth. That lasts often only a week or two, or sometimes three, and then usually it's nitrogen that runs out, because it takes a lot of nitrogen, just like growing any plants. And then it's phosphorus. And then after phosphorus, you have a number of other micronutrients.
Yeah.
And
But
of
the
course,
amazing thing about iron that Peter mentioned John Martin's work back in 1990, and the discovery that that one atom of iron will catalyze the life of 100,000 atoms of carbon. So iron is incredibly efficient. Just like that's one way of putting it. Like moles and the chemistry is and whether it is actually 100,000 or 10,000, but in any case, a tiny amount of iron will catalyze a vast amount of plankton growth. But Brian?
Well, let me just add that the original work from John Martin was about 1,000,000 to 1. So The good news is it doesn't matter whether it's 10,000 to 1 or 1,000,000 to 1. Iron is so cheap and that ratio is so high, it doesn't change the dynamics of the process between the 10,000 and the 1,000,000.
What about other things? Would you suggest adding nitrogen or phosphorus along with the iron?
That's something you do that in the testing. So with the nitrogen, you want to grow it yourself because it's expensive to produce nitrate fertilizer. And so at the mass that we need, 50 gigatons a year, you don't want to produce that much nitrogen fertilizer. But then when you come to the other elements, you might need some, and eventually people will figure out what's the most effective and efficient way to do that.
Right. That's a great question, Meta. In the subtropics, where Peter's proposing to do some of these trials, the nitrogen fixers can actually be helped by iron a bit, so they can likely provide a supply of nitrogen. It's likely that phosphate will be needed, but the good news is that phosphate's available just 100 or 150 meters down. As we've measured with our marine permaculture platforms, either through upwelling or deep cycling, it's possible to have a natural supply of phosphorus that can help to complement the micronutrients that Peter's proposing. And so it's quite likely that with local interventions, perhaps combining a number of approaches, that you can supply the macronutrients as well as the micronutrients that would be needed to sustain ocean productivity at its pre-industrial levels or greater. A couple other previous comments I'd like to bring in. One is that there are three mechanisms that are proposed for the Pinatubo effect of at least 7 gigatons of removal after the eruption. The first is local, as Peter's suggesting, local ash that could actually change the ocean dynamics in the ocean. The other is something we've mentioned previously, and that is 10% of the ocean's high nutrient, low chlorophyll. We know that the ash got up to the stratosphere. How much of that ash, and other aerosols would actually get to the high nutrient, low chlorophyll regions? That's a second mechanism. And the third is that we know that the Pinatubo and other eruptions cool the Earth. And when that Earth cools, you actually get a decrease in the Pacific equatorial current. And that reduced current means there's less upwelling over in the Eastern Pacific. And that actually translates to less outgassing of CO2. So all three of those have been proposed as Pinatubo mechanisms. And finally, I would mention that on Peter's curve that he put up, there's a green curve, and at least 7 gigatons occurred after the eruption. But the case has been made by a number of colleagues that almost half of the decrease might have actually occurred before June of 1991, if you look at Peter's green curve again. And that would, it raises something very interesting, which is that some of that decrease seemed to happen before, and at least 7 gigatons occurred after. So I think it's pretty clear there's an effect. And we just need to look at cause and effect and how much of it happened before, during, and after the eruption. Thanks.
I don't want to deflect this too far, but it sounds as if...
Let me just ask Brian. Sure. I hadn't heard that one before. Here's the graph. Here's Pinatubo. Right. And I don't see the evidence of removal before the eruption.
Yeah, look at the green curve that you've plotted. 1991 is a third of the way between the 1990 tick and the 1995 tick. And you'll notice that your green mass calculation of ppm is down by about a gigaton.
Oh, here.
Before June of 1991.
Yeah, so that was what's the word I want? When you have an El Nino, it starts with less CO2 emitted, and you can see that nicely in 1998. It's hard to see it here, but okay. Yeah, here you can see in before the 98 El Nino, you had a dip.
So and so the question is how much of the 17 gigatons might be associated with El Nino or other things? How much of it? Clearly, temporarily, there's at least 7 gigatons that have happened after Pinatubo, and parties may differ, but I think it's worth investigating. What are the mechanisms that Pinatubo seems to have contributed to?
Yeah, it's certainly a good scientific study.
What about other volcanoes?
Let me pull up the slide for that.
I think Peter has studied a lot of other volcanoes and volcanic eruptions. And there's a couple right now, by the way. There's one in Africa that's made its way all the way to India, and that's active right now. And some others going on. So we're living in interesting times.
There was a really big volcanic eruption in the Aleutian Islands near Alaska that added a lot of iron, and it just proved the salmon yield hypothesis.
Okay. Well, now, how much variation is there in the content of the stuff that gets thrown out by a volcano? Can we assume that all volcanoes have pretty much the same yield?
It varies a lot. Tonga, for example, had a huge amount of water vapor, but not a lot of other materials. So it behaved very differently than Pinatubo. So that giant Tonga eruption that was underwater put huge amounts of water vapor into the stratosphere, which had a very different effect than the Pinatubo eruption.
And the other thing about Pinatubo was that it injected a vast amount of sulfur into the stratosphere. And so it really kick-started the whole study of stratospheric aerosol injection, because the sulfur that Pinatubo added to the stratosphere cut the world temperature by 0.5 degree.
Mm-hmm.
So to answer your question about other eruptions, there were 9 eruptions that caused significant cooling in the atmosphere, that put significant amounts of aerosols into the atmosphere, and in the last 500 years. And of those, only 3 caused reductions in CO2. And so one, of course, is Pinatubo, which was very dramatic because we had the Mauna Loa data. Then in 1815, that Tambora removed about 6 parts per million. And then back in 1580, and Tambora is in Indonesia, Billy Mitchell around New Guinea was a huge one. It looks like 11 parts per million. And this is a graph extrapolated from the ice core data with their estimate of about 11 parts per million, or about almost 100 gigatons of CO2 removed. But of the other 6, none of them had any significant impact. on CO2 levels. And that was what the confirming data, or some confirming data, for the fact that it's downwelling eddies that do it. Because the other six either were land-locked volcanoes, or they were volcanoes like in Bali, where the ash fell into linear currents with with very, very rare eddies.
And the key thing here is that Peter is mimicking the natural process. So this biomimicry and volcano mimicry is a really key theme for how we can restore the climate.
It's actually so exciting, Peter. And it occurs to me that you're there in Silicon Valley, where all of these AI folks are. I have very ambivalent feelings about AI, and I mostly want to sort of shut them down, but I don't, because they help me all the time, every day. So I'm really really ambivalent about this, but it seems to me that you have friends, and you actually, you yourself have deep pockets. You have been a philanthropist, and you know these guys and stuff. Why don't you go calling on Mark Zuckerberg, or some of these guys, and say, you have a lot of influence with the U.S. government, and why don't you exactly start asking Trump for permission to let us do some local iron fertilization experiments? How about it, Peter?
Well, I've talked to a few of these billionaires, and although they like the idea, given their reputation and their wealth, they can't afford to be the first one. They can't afford the risk of being Russ George, and who was the first one to start doing it at a significant scale. And I can understand that. And so for that reason, we're working on some scientific papers. We're starting a million sponsor campaign for climate restoration. So the idea is to get 1 million people giving a penny, a dollar a month, or $100 a month, or $1 million a month if you're the kind of person who can do $100 million, $1 million a month. But get 1 million monthly sponsors, and that will send the message to the billionaires that it's safe now, because there's enough public support for doing it, and you're not going to be considered a rogue actor.
Okay. Well, okay, so you've thought ahead, you got a game plan, and I'm totally excited by it. I endorse it insofar as maybe a host shouldn't take sides, but I'm definitely on your side. You guys, how about you?
What's the other side?
Just one final comment, and that is that a lot of that money needs to go into advocacy, because there are big NGOs who've got quite a lot of money who are campaigning against this work. And so like Greenpeace and Heinrich Böll in Germany. And there needs to be an organised publicity and explanation advocacy campaign that needs to be well funded and organised in order to get the public information and permissions and support that will then catalyse the investment in the testing as next steps.
You're right, absolutely.
Yeah.
So we're all for that. Thank you, all of you. I think this has been thrilling, and it's also fun to be back together with you and see you're chugging ahead, continuing the work. So it's marvelous.
Thank you, Meta.